Welcome to section 4.6, Systems of Nonlinear Equations. Our solution techniques, if you consult the notes, are very similar to the solution techniques that we used in chapter 2 to solve systems of linear equations. We are just going to extend those ideas now that we have some more sophisticated equation solving techniques. Now we can solve more interesting systems of equations. So here we have one example of a nonlinear, or a system of nonlinear equations. We can see one of these is quadratic, and one of them is linear. So the first approach that we're going to use is to solve by graphing. So I will utilize my graphing calculator to solve this problem. If we type in each of these functions, they're already in terms of y, so we can just type 2x squared minus 9 in for y1, and 4x minus 3 in for y2. And if we hit graph, we are going to see that we have a parabola and a line. That's not surprising. We know the basic shapes that these two curves will take. And the solutions to this system are going to be points which are solutions to each equation, just like before. So what we are interested in finding is the points which lie on both curves, in other words, the intersection points. And so just like back in chapter 2, we're going to find those intersection points by using the intersection feature of your graphing calculator. Now, if you're using a standard window, you can see that the intersection points don't really fall within the window that we can see. Now, if you're viewing these points with a standard window, chances are that you can't really see one of the points very well. You can see the left intersection point fairly well, but the right one is a little bit muddled. So I'm going to adjust my window very slightly. I'll change my Y max so I can see a little bit higher. I'll go up to 15. That should give me plenty of room. That's better. Now we can see both intersections a little more clearly. So I'll find the left intersection point first. Second calc, find the intersect, and we can see there that the cursor is on the parabola to begin with, and then it jumps to the line, and then our guess will be somewhere over here near where the intersection appears to be. Well, the intersection point at that end is -1, -7. Let's get into finding the other. So I'll do the same procedure. Second, calculate. Option 5 is the intersect. And at the moment we're on the parabola. And then if we select that, we jump to the line, select that, and come over near that other intersection point. Now back when we were solving linear systems in this way, we didn't have to be very specific, very careful with our guess. But now we can have multiple intersection points, so we have to be a little more careful to get near the point we actually want. And that intersection point is at 3, 9. Alright, let's check these really quickly. I want to verify that both of these are solutions to the system. Well, if y equals -7, and I'm plugging this into the top equation first, is that equal to 2 times -1 squared minus 9? Well, 2 times -1 squared is 2 times 1 minus 9, so this is 2 minus 9, which is -7. So that is equal. And that point is in fact a solution. So -1, -7 works in the top equation. Let's try it in the bottom equation. So -7 for y, is that equal to 4 times -1 minus 3? Well, negative 4 minus 3 is equal to negative 7. So that checks out, and that point is a winner. Alright, let's check the other point, 3, 9, in both equations. We want to plug 9 in for y, and 2 times 3 squared minus 9, well that's 2 times 9 minus 9, that's 18 minus 9, which is 9. And so those are equal to each other. And we'll plug that into the other equation that we're trying to solve, is 9, well, let's not say it's equal just yet. Let's say 4 times 3 minus 3, well that's 12 minus 3, which is 9, so these are in fact equal. And this point is also a solution. So that's how we'll check. If we have a point that we think is a solution, we plug it into every equation in the system, and if it satisfies every equation, then it is indeed a solution. If any equation is not satisfied by that point, then that point is not actually a solution to the system. So as we saw, our systems can have multiple solutions now. So let's take a look at another one. This time we're going to solve by substitution. Now in substitution, we pick one equation and one variable, and then we solve for that variable within that equation. In this system, the bottom equation is already solved in terms of y. So I can substitute x minus 1 in for y in the other equation. So what will that look like? We'll get x squared plus, instead of y, we're going to use x minus 1 and square that, equals 1. And now we have an equation simply involving the variable x, which we can solve now using some of our more advanced solution techniques. Well, this, if we look at it a little bit further, if we square x minus 1, remember we have to FOIL, so we would get x squared minus 2x plus 1 equals 1. And if you want to do the side work for that, x minus 1 equals x squared minus x plus 1, which gives us x squared minus 2x plus 1. Alright, well we don't really need those parentheses anymore. In fact, we could combine some like terms. We have x squared and x squared, 2x squared, minus 2x plus 1 equals 1. And since what we're dealing with here is a quadratic, we probably want to move that 1 over to the other side, get one side equal to 0, and put it in standard form. So 2x squared minus 2x is equal to 0. Now take a moment and see if you can tell where we're going to go from here. This is a quadratic, so our first approach might be to try to factor. And the simplest version of factoring is to factor anything common to every term out. Notice we have a 2 in every term and we have an x in every term. So we can get 2x out. And what are we going to be left with? Well, if I factor out one of the x's, I'm left with the other x here. And I'm factoring all of that second term out, so I'll be left with a 1. So the zero product property says that either x equals 0 or x equals 1. Well, we're not quite done. We found values for x, but now we need to take those x values and find the corresponding y value that goes with them. So if I wanted to substitute x back into one of these equations, I'll look at x equals 0 first. I'm going to substitute x equals 0 into one of my equations. I think the bottom equation, equation number 2 here, is going to be a little bit easier. So to solve for y, we get y equals 0 minus 1. And it looks like y equals negative 1. So the point that we came up with is 0, negative 1. On the other hand, if x equals 1, we'll substitute that in to y equals x minus 1. and that'll give us y equals 1 minus 1. In other words, y equals 0. So we get a second point, 1, 0, that should also satisfy this system. So let's check both of those. We're going to be a little pressed for room here. Well, if I check 0, 1 in the first equation, 0 squared, or 0 negative 1 rather, plus negative 1 squared, well, that's equal to 0 plus negative 1 squared is just 1. So this is equal to 1, which is what we're trying to achieve. So this one works in the first equation. In the second equation, y, negative 1, and if we plug in x equals 0, then we have a fairly obvious equality. So this point is one solution, and if we check the other point, x, 1 squared, plus y, 0 squared, well, that's equal to 1, pretty obviously. So that satisfies the first equation, and if we plug those x and y values into the second equation, we get, let's see, y is 0, and x is 1 minus 1, so that is definitely also true. So the checking on these is usually very straightforward, pretty simple. Sometimes it can get a little complicated, but it's always worthwhile to make sure that we did everything up to that point correctly. This is a good way to find any errors that we made in the process. Now, to kind of visualize what we're seeing here, we can think of the graphical version of this system. The top equation, x squared plus y squared equals 1, well, that is a circle centered at the origin with a radius of 1. So if you put 1, 1, negative 1, negative 1, we would have a circle. Alright, so that's x squared plus y squared equals 1. Our other equation, that's something we've been able to graph from the very beginning. Y equals x minus 1, that's a line with a y-intercept at negative 1 and a slope of 1. So there we see our two intersection points. It's a little tough to see on here, but if you graph both of those equations on graph paper, nice big picture, you'll be able to see that intersection point very easily, or those intersection points very easily. Here we see another system of nonlinear equations. This time we're going to solve using the elimination approach. Now elimination, while handy and somewhat nicer looking, in some folks' opinions, is only really appropriate when your equations share the same form. So here we have an x squared, a y squared, and in the second equation we also have an x squared and a y squared and nothing else. So we can stack those, as we have here, and get our coefficients in one of those variables or the other to match, but have opposite signs. So we could begin by multiplying the bottom equation by negative 1, which would leave us with x squared plus 2y squared equals 2, and negative x squared minus y squared equals negative 1. Now if we add, we'll eliminate the x squareds, and we have 2y squared minus y squared, leaving us with y squared only. And on the right hand side, 2 minus 1 leaves us with 1. So now we can solve this equation, in this case for y, since x was eliminated. If we square root both sides, we see that y is a positive or negative square root of 1. In other words, positive or negative 1. Alright, now we need to figure out what x value corresponds with each of these y values. For 1, we are going to plug this back into one or the other of our equations. I have a feeling that the bottom equation will be a little bit easier. So if we plug y equals 1 in, now we have another equation in terms of one variable only. So x squared plus 1 is equal to 1, and we can subtract 1 to the other side, and we see that x squared equals 0. So again, we can square root both sides of this, so x equals positive or negative square root of 0. Well, that's a little bit odd, but positive or negative 0 is 0. So our solution point, 0, 1, in this case, and we'll check that when we're all finished. Now our other y value, y equals negative 1, if we plug that into the bottom equation, x squared plus negative 1 squared equals 1. Our solution process from here on in is going to look very similar. When we square negative 1, we get 1. And this line matches this line exactly. So all of our steps after this are going to look the same, and our result will be the same, x equals 0. So we get two solution points, 0, 1, and 0, negative 1. So let's check those in both equations. 0, 1, we'll check that one first. In the top equation, is 0 squared plus 2 times 1 squared. Well, that's equal to 0 plus 2, which is 2. Well, that's equal to 2. So that checks out in the first equation. The second equation will look pretty similar. If we square 0 and we square 1, then we get 0 plus 1, which is 1, which equals 1. And we satisfied the second equation. Now we'll check the other point, 0, negative 1, in the first equation. So if we plug in 0 for x, we get 0 squared plus 2 times negative 1 squared. That's 0 plus 2 times 1, which is equal to 2. In our second equation, 0 squared plus negative 1 squared, well, that is equal to 0 plus 1, which is equal to 1. So both of these points satisfy, and that's our solution to this system. Now, elimination, as we said, would not have worked if we had x squareds and x's in one of these equations, but not the other. So we have to have all of the same components to our equation in order to stack them in this way and get one variable to eliminate. So elimination is useful and relatively nice, but not always appropriate now that we're dealing with systems of nonlinear equations. Here we see another system which we will solve using elimination, since we have x squared and y squared in both equations and no other variables. Now, if we make the bottom equation negative, if we multiply both sides by a negative, our system becomes x squared plus y squared equals 9, and negative x squared minus y squared equals negative 1. So if we add these together, our resulting equation is 0 plus 0 equals 8. So 0 equals 8, well, that's not true. So our initial assumption that these two equations could be satisfied by the same pair x and y is false. We would say there is no solution. So the contradiction that we encountered here implies that there is no solution to the system. And this goes back to exactly the same concept that we saw when we solved systems of linear equations. When you end up with something nonsensical, all of your variables canceling, and you end up with an equation you cannot solve, if that equation is false, then there's no solution. If the equation is true, then we would say there are infinitely many solutions, because the graphs that we're looking at are both the same. For instance, if we solve this next system of equations. Now we would begin by trying to pick a variable that we wish to eliminate, and then multiplying as necessary to ensure that the coefficients are such that that variable does in fact eliminate when we add. So I think we'll multiply the top equation by -2. That gives us -2x squared minus 2y squared equals -8. And our bottom equation is still 2x squared plus 2y squared equals 8. So when we add these together, we see that 0 equals 0. And this implies that there are infinitely many solutions. In fact, even more powerfully, it implies that these are the same equation. And we can see that x squared plus y squared equals 4. If we divide this equation by 2, we get x squared plus y squared on the left and 4 on the right. So these are identical equations, and asking where the graphs of these equations overlap is going to return the result every point on either graph. Now, another nice way to think of the first example on this page, the top equation represents a circle centered at the origin with a radius of 3. So 1, 2, 3, 1, 2, 3. Circle may not be very circular, but our second equation, x squared plus y squared equals 1, that is a circle also centered at the origin with a radius of 1. Then we can see there are no points shared by either of these circles. Alright. So that's a sort of graphical interpretation of this system. We already solved it using elimination. We know there's no solution, but the reason behind it is, or can be visualized in this way. So that's how we'll determine if there are either no solutions or infinitely many solutions using the exact same thought process that we used back in Chapter 2. And those are all of the concepts for this section. Take a look at those homework problems and bring any questions that you have to class.